This is top 9 ways to factor. And it's top 9 because there's 9 problems. That's about it. So if you start to analyze this by the number of terms it has, you'll find that some of these have 2 terms. These 2, this one, okay? Some of them have 3 terms, like this one, and this one, this one, this one, and this one. And one of them has 4 terms. So if you start to do them in the way that they're grouped, it's a little bit easier. Now, overall, the number one thing you always want to do is to factor out a GCF first. GCF, that's greatest common factor. That means the biggest number that can divide evenly into all of the numbers. So let's see if that works on number 1. So number 1, 3 and 12. I know it says negative 12, but I'm just focused on the number part. 3 and 12. That's divisible by 3. So we write a 3 out in front, and we divide each of those by 3. So the first term becomes x squared. The second term becomes minus 4. Now we'll come back to that in a second, but let's do it again for number 2. 81 and 9, greatest common factor, 9. So 9 times 9x minus 1. Oops, 9x squared minus 1. We'll come back to that. But is the answer to the GCF just you always take the smaller number? No, here's an example with 12 and 14, number 4. 12 and 14, greatest common factor, 2. Biggest number that divides evenly into 12 and 14. So we write a 2 out in front. We've got 6x squared plus 7. Now, inside the parentheses, you see if you can factor it more. On number 4, that's it. That doesn't match any of our patterns. That's already factored. End of story. However, number 1 has a pattern we call the difference of squares pattern. It has a perfect square minus a perfect square. So we write the 3, and then it kind of looks like a battery. It has a plus and a minus. And you fill in those with the square roots. So the square root of x squared is x. The square root of 4 is 2. And there you go, completely factored. And for number 2, okay, so you always write the greatest common factor as part of the answer. And the square root of 9x squared is 3x. And the square root of 1 is 1. And there we are, we're completely factored. Now let's take one of these 3-term expressions and see if we can figure something out. So first of all, GCF. I don't see one on 3, I don't see one on 5 or 6 or 7, but on number 9, well, all of those are divisible by 2. So I take that out, and that'll be x squared plus 2x plus 1. Okay, here's another pattern to look for. It's called the perfect square pattern. Now, let me do this off to the side here. If you have a perfect square, and we'll use the box to illustrate that, that's a plus b and a plus b. You'll have a squared, an ab here, an ab here, and a b squared at the end. So a squared plus 2ab plus b squared. So what are the clues I should be looking for here? Well, it ends and starts with a perfect square. Perfect squares. Then the middle is going to be the square root of those two numbers, or two expressions, and it will be doubled. So let's take a look through and see if we see the perfect squares pattern there. On number 3, no, because you have 20. That's not a perfect square. Number 5, 4 is a perfect square, but 3 is not out in front. 6 is not. 7, okay, now look. X squared and 64 is 8 squared. So if you took the square root of x squared, that's x. If you took the square root of 64, that's 8. And if you doubled it, do you get the middle? Yeah, you get the middle, except it's negative 16. So that means in our perfect square, which we're going to fill in with now a minus sign, because there's a minus in the second coefficient, we just fill it in with the perfect square roots. So that would be x and 8. And this one is done. Now number 9 actually does have a perfect square after the GCF. X squared plus 2x plus 1 is x squared and 1 squared, and sure enough, the middle is doubled. So you would take 2, fill it in with a plus, we're going to square it, and the square root of x squared is x, and the square root of 1 is 1. All right, we're really knocking them down. We're more than halfway there. Now let's look for problems that start with 1x squared and are factorable. That means that the last number and the middle number, we can undo the riddle. We can say, can I think of two numbers that multiply to 20 and add to 9? And yes, we can, 5 and 4. So that would be x plus 5 and x plus 4. And there we go. 2 left to do. Now number 5 starts with a 3. Number 6 doesn't. So let's look at number 6. Is there a number that will multiply to -1 that adds to -1? Or actually two numbers that do that. It doesn't seem very likely. But maybe we're just having an off day, a bad day. Well, there is a way to check to see if this is factorable. You take a piece of the quadratic formula. You take b squared minus 4ac, and you apply it to the expression. So that would be -1 squared minus 4 times 1 times -1. And this gives you 1 plus 4 times 1, essentially. A couple of 1s. So this is 5. Now here's the rule. If b squared minus 4ac is a perfect square, then it's factorable. What's a perfect square? That's numbers like 1, 4, 9, 16, 25, 36. In other words, numbers multiplied by themselves give you these. This is 1 times 1, 2 times 2, 3 times 3, 4 times 4, 5 times 5, etc. So 5 is not a perfect square. That means that this polynomial is not factorable. So a lot of times people will write that as their answer. They'll just say not factorable. I can't do it. But sometimes also people will write prime, because a polynomial can be prime if it is not factorable, just like numbers. Check to see which one your teacher prefers. Okay, now we've come down to number 5. It's not a perfect square. It's not a difference of squares. It doesn't start with 1x squared. How do we factor it? Well, we can use the familiar x with a little modification. Make a crossbar. Now, put the leading coefficient of 3 in the corners, upper left-hand, upper right-hand corners. Take the first number times the last number, put that on top. Take the middle number, put that on the bottom. Now ask yourself, are there any two numbers that multiply to 12 that add just 13? And the answer is yes, 1 and 12. Now, if you're going to use the box method, then you have all the information you need to do the box. But there's also a shortcut here. If we look at this as a fraction and say, is that reduced? That is reduced. Now, you take the 3 as the coefficient of x and the 1 as the constant, and that's the term. Or rather, that's the factor. Then you take 3 over 12 and say, if that was a fraction, is that reduced? No, it would have to be 1 over 4 to be reduced. Then this would be x plus 4. And there you go. It's all factored. That is one of many ways to factor. Number 8. Unique because it has 4 terms. So, if it's going to factor, here's how it factors. Look at 2 terms at a time and take out the GCF. So the first 2 terms have a common factor of x squared, and that would leave behind, in other words, if you do the distributive property, what could get you back to where you were would be an x minus 8. And for the next 2 terms, take the minus with the 3. And 3 goes into 24 8 times. So this would be x minus 8. You see how they both have x minus 8? Well, that is mandatory. We need that to happen. If that doesn't happen, it's not factorable. So x minus 8 is in common between those 2 terms. And if you let's say, what does that leave behind when I take out x minus 8? It leaves behind x squared and minus 3. Well, you also need to check and make sure that what's left isn't factorable. And in this case, it's not. So we're done. That's it. This one is called factor by grouping. Factor by grouping. And that's it. Top 9 ways to factor.